Thank you, everybody, for joining us today. We are excited to announce one of our newest products, which is an accessory to the Ultium system, one of our SmartLeads, which is the Ultium Insole. So today we are going to be discussing some of the technical aspects of the insole, just to give everyone an understanding of how these are constructed and what data they provide. And then we'll take a look at a couple different examples of how these insoles could be utilized within the multi-device concept inside of the MR software. So for those of you who are new to our webinar series, please feel free to ask any questions as we're going through. You can post them into the Q&A section of the Zoom meeting, or you can also post them into the chat box, as we will be moderating both of those for the question and answer section at the end of the presentation. So let's go ahead and get started. So first, let's talk about the background. So why did we create these? So obviously, instrumented insoles are broadly used in biomechanics for understanding how force or pressure is distributed amongst the plantar surface of the foot. This can provide valuable information that traditionally has been used in a clinical sense for looking at diabetic and foot, and also potentially for the creation of orthotics, but has also been utilized in sports as well as performance settings to help optimize different techniques, or really understand how people are accepting load or transferring load in certain dynamic activities. Those could be utilized to help reduce the risk of injury, or change different aspects of their movement to gain certain performance advantages. So we created the Ultium insole because we wanted to have something that was a higher level than your basic foot switch, that allowed for people to understand things like the timing. When is the foot on and off of the ground? Just as the foot switch would, but then also to provide some qualitative impact characteristics, so that you can understand that strategy of the loading parameter. How are people coming in contact with the ground, and what portions of the foot are they utilizing to produce those movements? And the idea was we wanted something that would fit within our multi-device concept, be fairly affordable for folks to be able to add on to their system easily. And then, of course, create something that was simple to use, so there was minimal technical effort in terms of using this device alongside any of the other systems that you might have. So the target markets that we've been looking at for this device has primarily been in the sports and medical side of things. So looking at things like gait analysis, running, static and dynamic loading asymmetries, sway analysis. This could also be utilized in ergonomics as well, so looking at load transfers. And then, of course, all of those could encompass some of our research topics as well. But typically, this device is going to be used alongside some other aspects, such as EMG or kinematics, to be able to capture and segment that data and understand, again, what's going on from the plantar surface all the way up through the chain, whether that's through the neuromuscular aspects of EMG, the dynamic ranges of motion from motion capture, or even including things like, such as video. Seems my computer is moving a little bit slow. Here we go. So let's talk about some of the technical specifications. So first and foremost, the insole is set up as an 8-zone with eight zones of resistive pressure sensors. So these are sensors that allow us to have a high frequency. So you can see there that we're able to sample at 250 or 500 hertz for the 8 zones, or if you use one of the masks, you can even upsample that to 500 or 1000 hertz. The difference between those two is what you have the Ultium system set at. So the Ultium system is able to capture at 2000 or 4000 hertz. And so depending on which setting you have, those are going to be your options for sampling frequency for these insoles. The measurement range is looking at 0 to 75 psi, and that's our calibrated range. However, there is a max pressure of 100 psi before failure, which could potentially cause damage to the sensors. Through our calibration and through our testing, we've noticed a hysteresis of less than 5%. We have a root mean square error of less than 3% full scale, and then also a between zone variation of less than 5% full scale. For the life expectancy, these insoles are meant to be reusable, but eventually will degrade over time, especially depending on what type of use they're being used with. So for light impacts, we're expecting 500,000 cycles unloading and loading for each one of the sensors. And then heavy impacts, we're looking at about 50,000 cycles. So again, that plays into the factor of having them, be this affordable product that you can utilize for a certain amount of time, but then, it's not going to break the bank when you need to be able to purchase additional insoles for your projects. So of course, the dimensions here, you can see of the SmartLead as well as the weight, just so you have an understanding. And then we've got some aspects looking at the sizing. So we've got essentially 4 sizes here: a small, medium, large, and extra large, which you can see there encapsulate the different European and US men's and women's shoe sizes. And then we've got some information here shown for the actual measurement of the insole, as well as the different weights here. So of course, the larger that they get, the heavier that they might be. But to be quite honest, these are not really that heavy at all. Once you have them in the shoe, it's tough to notice that they're there. So if we look at how the different sensors are set up within the insole, we've got this breakdown shown here on the left. And so these are where the position of the sensors are. So we've got a separation of the heel. We have one set up at the arch, or the midfoot region rather, to show when that portion of the foot is in contact. A separation of 3 metatarsal heads, so not the entire 5, but a good capture of the general aspects of the metatarsal heads. And then we've got the hallux and the toes to be able to capture when those portions of the foot are in contact as well. As I mentioned earlier, we are able to apply some masks, so you can reduce these to, instead of having 8 zones, you can look at 4 zones, and those can be set up as you see in the red boxes here. So we've got the anterior-posterior positioning, or we've got the option to look at sort of like a medial-lateral positioning. So again, if we do increase those, we do apply those masks, it allows us to increase that sampling rate and be able to look at the individual zones with a little bit more data, as opposed to the 8 zones, which are limited to the 250 or 500 hertz samples. So some of the features and the benefits of this system. So first we'll talk about what kind of data this system provides. So it's an affordable solution, of course, looking at the contact detection and the quantitative and qualitative impact characteristics in gait and running, as well as that relative or normalized load distribution during different bilateral or unilateral activities. As far as what data is actually provided, it's important to understand that we are providing a normalized load curve. So aside from some of the qualitative representations of the data, such as the pressure animation here, or the center of pressure trace, we also have these load time curves, which are normalized to body weight following a short calibration before each of the recordings. That's important to understand because some other insoles that are on the market are going to provide a absolute measurement of force. As many of you might understand, there's some high variability in providing that type of data. We wanted to avoid that and provide our users with something that can be looked upon to compare within subjects, as well as give the ability to look at it with respect to the body weight, so that you can understand that loading as it relates to the individual. Due to that variability in the sensors, as well as some of the aspects with calculating force from pressure and the variability there, that's why we decided to go with the normalized load across the 8 zones, as opposed to that discrete value of absolute force. The information certainly can still be utilized to look at those loading characteristics, but the main aspects of this system are to be able to understand the impact characteristics from a qualitative standpoint, and then of course to be able to use these with the multi-device concept, so that you can characterize the other data that you're looking at as it relates to that planar pressure development or planar pressure distribution. So we'll take a look at this information here in just a minute. As far as timing characteristics, so we've done some testing internally to provide some of these values here. So you can see for our most recent test with 96 contacts evaluated, we have a onset timing of 8.5 plus or minus 5 milliseconds, which would be a 2% body weight threshold, and then the offset at about 9.5 plus or minus 14 milliseconds. So definitely a little bit more variability on the offset side of things when we compare it to a force plate. But that's to be expected, as of course with the force plate, once you come off of it, you're not measuring that direct point of contact any longer, and of course there's a higher sampling frequency there as well. The in-shoe measurements, you still might have a little bit of lag from potentially the toes coming in contact, or the hallux coming in contact with those sensors at the front end of the insole. Some other things that you would potentially want to look out for would be, having the shoes be too tight, for instance, which can cause some phantom pressures, if you will. So this would be a representation of that load time curve. So as I mentioned, we do have it set up as a body weight normalized curve. And so there's a calibration that takes place before the measurement. There are the options to, again, apply the masks or the entire zones, and we do provide individual curves for each one of the zones that are selected. Of course, you have the freedom, whether you have the masks turned on or not, to select or deselect any of those different zones. And just as a comparison here, I've got a graph shown on the right, looking at the M curves from a gait trial, where we've got force coming from a instrumented pressure treadmill, as well as force coming from load cells, which are also part of that instrumented treadmill. And then finally down below is the M curve from the insoles. So one thing to note, as far as the shape, I mean, we're there. The timing is also very close as well, which we just reviewed. But there are some aspects that you want to pay attention to in terms of how this shape takes place and where some of those peak values are occurring. This can obviously be affected by that calibration, so it's important to maintain a good calibration. And the process for that's quite simple. It just requires the individual to stand on each foot for just a second or so. But if they do hold on to something or reduce that body weight pressure, that can have an effect on the data going forward. So definitely something to pay attention to when utilizing these. Now, if we look at the center of pressure accuracy, of course, with these insoles, we're only working with 8 sensors. So it's fairly low resolution in terms of capturing the center of pressure, but we've been able to demonstrate some good results in terms of the shape of the center of pressure plots. And we've got some information here demonstrating the root mean squared error, which you can see as we get towards the toes, where there's going to be more feet or more portions of the foot in contact with the ground, and something with a little bit higher spatial resolution might capture that slight deviation. With the 8 sensors, we're limited in our ability to capture that deviation. So you can see as we get later down into the towards the toes, there's a little bit higher error margin that we're seeing both in the X direction and the Y direction. However, if we look over to the right here, these are the plots of the center of pressure. This one coming from the insoles, and the one on the right coming from a pressure treadmill. So in general, we're seeing the nice similar shape here, but this is where some of that error starts to occur, where there might be some certain roll-off occurring at the metatarsal heads or right before the toes, which again, with the lower resolution, we're not able to capture fully, but it should still give some nice qualitative information for understanding that strategy of the loading and where that pressure, that center of pressure, is occurring at a certain point in time. In addition, I've got some examples here showing walking. So we can see again similar shape that's being followed, and then running as well. Probably with running, you'll see closer accuracy towards something with a little bit higher spatial resolution. Typically, just because there's not as much contact going on with the foot, where there's play happening with certain roll-off factors, up towards those metatarsal heads. Whereas in gait, again, you've got a little bit more going on here at those metatarsal heads, and then ultimately the toe, to be able to see that center of pressure sort of deviate a little bit around here. Of course, with the insoles, we're just basically capturing that trajectory of it, moving from the heel, kind of coming in towards that midfoot area, capturing the center portion of the metatarsals, and then ultimately that toe off there. So one thing I want to discuss is just some general comparisons. So basically for what we have available within our concept, we've got 3 options. And so we're discussing the Ultium Insoles here, which are going to give us information about those loading or those impact characteristics. We do not have the force time curve, but we do look at the loading as it relates to the left and the right, and of course, normalized to that calibration and that body weight. We've got the center of pressure trace. We have the option to look at timing or contact detection. It's compatible with the portable lab system, so that you can utilize it with your Ultium or your motion system. And we're probably in that medium budget range. So it's an affordable option to really graduate to the next level, aside from just looking at timing, but then also looking at some of these impact characteristics. If we were to go up a level, we would look at something that's got a bit more higher spatial resolution. And within our product family, we've got the Metalogic insoles. And so, very similar in terms of what type of information it's providing, but then it also gives us a force time curve. So a little bit different in terms of the data. And this would be the solution that if you were interested in looking at those force characteristics, you'd want to have that high resolution data and the individual sensor calibration that these go through in order to produce that information. And then finally, on the lower end, of course, we've got our foot switches. So with these, obviously, you're just looking at timing and contact detection. They're certainly compatible with the multi-device concept, but they are limited in what you're able to do with them. And then, of course, that kind of falls in that low budget category. So these would be generally the three options to look at in terms of understanding how the foot is coming in contact with the ground. And you, within our concept or within our product family, you've got that ability to choose that variation of what makes the most sense for you. I would think in most cases, where folks are not necessarily focused on the forces, but really just want to understand that loading strategy, and have it be related to some of the other data that might be captured. The Ultium insoles are going to be a great solution to add into that mix, so that you can have that information about when the foot is in contact with the ground, as well as how is it coming in contact with the ground. So for that, I'm going to go ahead and jump over into MR3, and we're going to take a look at a couple examples here of using the system. So first, let's go ahead and let's take a look at a gate record. So this is going to be utilized with the multi-device system. So you can see here, we've got video, we've got motion, and we've got the insole system. So to start, we can obviously play this back inside MR3. We've got full control over this 3D animation to look at it in different viewpoints if we want to see that side view of how those pressures are developing. But then obviously we can look at the top view as well. We can slow these down and play it back and really see how that load is transferring during gate. And we can even enable that center of pressure to be able to look at how the pressure is being handled for each step. As far as the data that's being provided, you can see over on the left here, I've got the different curves pulled out. And this is an example of the load curve, which again is normalized to that body weight from the calibration there. And then the different separations of the zones. Each one of these is its own signal, so we can pop it out into its own window and really see when that, what's going on in terms of how much load is that portion of the foot accepting during this task. And then obviously we've got a total or a maximum, curve as well, which can show us that traditional M style that we might see during gate, or something of loading where we're looking at running and it's a bit more of a higher peak. Something that we're able to do then with this information, of course, is utilize it within the multi-device concept. So here we've also got the motion system. So in this case, maybe we would want to look at, okay, how do these, does the loading, either the rate of loading or the timing of the loading, relate to the kinematics, for instance? So in this case, I'm just going to pull out this left maximum signal here. And then let's grab one of our kinematic angles and take a look at how those relate. So for instance, if we look at knee flexion and ankle dorsiflexion and hip flexion, as it relates to these, we can utilize the viewer inside MR3 to overlay these signals and start to understand some of those different relationships here. So as far as the timing is concerned, we can see, okay, upon that initial contact, we're landing with a little bit of hip flexion. We've got some plantar flexion going on at the ankle, and then of course some knee flexion to accept that. As we get to that first peak of the M curve, which might be a point of interest for some individuals, you're able to understand, okay, how are things transitioning from a kinematic perspective? The next stage in this, aside from using it within the viewer, is of course then you running a report. Having the insoles allows us to then segment this data so that we can look at it in an average curve, the context of an average curve. So for instance, let's go ahead and take a look at the walking gait here. And I will go ahead and choose our Ultium Insole gait report. So we can utilize those signals to define the stance in the swing phase, which you can see are lined up here. Of course, I've got my left side called out, and so this is indicating that left stance. If we go back to the other side where we've got our right side, you can see how those are signified as well. So if we just step through here and run the report, and we can take a look at the average pressure print. So that's giving us an understanding of how, basically an average of each one of the steps, giving us a sample of the center pressure curve, as well as the different hot spots or average pressure spots that we're seeing. We can plot the load time curves here on the left and the right. We can look at the individual center of pressure diagrams, so each step overlaid on top of one another, basically giving us that variability, as well as things like single support phase here. We've got options for looking at the length of the gate line, which of course, you can see that percentage difference if there's a significant difference there. Breaking down the gate phases, so allowing us to understand the temporal aspects of gate and how they might differ between the two sides. Some other additional temporal parameters such as step time and stride time and cadence. And then of course the breakdown of the kinematics, or if you have EMG involved, that might be another aspect to look at as well. So having the insole again allows us to segment that data so that not only can we understand the loading characteristics of it, but then also how does that relate to the kinematics or potentially even the muscle firing patterns. One thing that's pretty interesting about this particular record is we see that there's definitely a little bit more of a higher pressure at the hallux here on the right side. We can even see that indicated with the increase in this peak on the red curve there. If we go down to ankle inversion, for instance, this is something that allows us to relate what we're seeing from the pressure information to then the kinematics. And in this particular case, on this right side, we're able to see that we get much more ankle inversion coming towards the end of terminal stance here. And that's what's creating that additional pressure at the toe. Now, that may or may not be what you're searching for from an individual, but in general, you can see that there's some sort of asymmetry or discrepancy there. So, if that potentially is causing them pain, or for instance, they are having some issues with walking, these would be ways that you would be able to highlight and document those objective changes. And then of course, work with them, let's say, if you're in the clinic, to be able to adjust that and reduce that asymmetry such that the loading characteristics as well as the kinematics are similar between the two sides. Some other examples might be looking at things like balance, for instance. So if we were to look at, something like creating a best test, where we would look at in-shoe pressure measurements and then potentially relate that to other aspects. For instance, in this particular case, we have set up some EMG where we're looking at in this case, the dominant leg, but we're looking at basically the chain of command in terms of neuromuscular firing, where we've got ankle stability controlled by the soleus, some knee and hip stability controlled by some quad activation, and then trunk controlled by the lumbar spine. Definitely, for the initial portion of the best test, where it's just a simple double leg stance, we can see that we're relatively low in terms of our signals. Of course, we've got some activity going on at the soleus, kind of maintaining that ankle stability when the eyes are closed, slight activation of the quad here, and essentially quiet from the trunk. As we move into that single leg, you can see there's a significant increase in both the soleus activation as well as the quad activation. One thing that I think is interesting about this setup, and it can be really nice to utilize in terms of this type of clinical test, is if you have something simple such as the 2 insoles, maybe 3 or 4 channels of EMG, you can really get a good quantitative analysis of something like the best test or any other type of balance exam. And in particular, with the lumbar spine, I think what's interesting here is we're able to basically see points of time where that trunk deviation is moving. And obviously, in terms of that clinical test for the best test, that would be one of those error scores that you would mark. So having this as a documentation allows you to see, okay, what is that person's ability to control their trunk, as well as how do they handle balance, at the quad level or the knee and the hip level, and then of course at the ankle. And then finally, moving into the tandem stance here, you can see again we get some more trunk stability, but having a little bit of that ankle movement as well as the quad. That we're seeing some movement at the knee and the hip. One thing to note, if we go back, so this is of course on the firm surface. If we take a look at the foam surface, we can see how things change a little bit, right? So in this case, we've got our soleus or our ankle activation here. Definitely, even in double stance with that foam, it's having to be a little bit more responsive in keeping and maintaining that proprioceptive balance. There's even some cases, again, indicating that trunk movement here with the lumbar spine activation. As we go into things like the tandem test, you can see these huge increases in some of the lumbar spine, which of course, would indicate that falling aspect. I think what's interesting to see then, is how does that relate to then the pressures that we're looking at from the insoles here. So if we take a look at, even just this tandem test, let me take a step back and play this kind of in repeat. So we can see, of course, that we're looking at the left foot. There's definitely some significant pressures going on the left side, kind of maintaining that balance with the right foot helping out. But during those particular points where we're seeing that person, touch down or fall or leave that portion of the movement, you can see what starts to happen. So there's some significant deviation in what's going on with the pressure. And then, of course, this gives you that documentation to be able to see, okay, was that person out of position for longer than 5 seconds? Again, allowing you to mark that error. Of course, in this particular setup, we could also include video. So that would be another aspect to have. What I utilize in this particular recording, you can see we've got some segmented data points here, but that's really one of our setups that we're able to do with the sequence testing. That you can design and build inside of MR3. So this would be an example of how to use this multi-device setup plus some of the software features to create some sort of clinical test that you can utilize for your own documentation purposes. Of course, at that point, what we're able to do is then even create a report, which let me see where I have it, the best test. And we can set it up such that we've got, and forgive me, my computer has been running a little bit slow lately, so give me a second here. But we're able to then pull out the data from the different segments and not only see things such as the pressure print and what that center pressure deviation looks like at each one of the sections, but then, some information about, in this case, the EMG. And we should be pulling up. So this would be an example of how to create then a customized report utilizing this information to be able to create that documentation for yourself. So in this case, we've got our double leg stance. We can see, we've got certainly some deviation going on here, but generally a nice, tight circle in between the 2 feet. Of course, looking at then the EMG information and then some statistical parameters of that. Moving to the single leg stance, we can see, of course, a lot of anterior posterior movement for this individual in the single leg stance, and this is on the foam surface, so significantly more movement probably than the firm surface. And then even some indication of sometimes if there was a toe down or touching down on the other side of the foot when there shouldn't be. Again, having those statistics. And then in this case, whoops, this should not be flexion relaxation, but rather the tandem stance. Let's change that real quick. So then the tandem stance, which again, we can see, some deviation kind of going in this diagonal position, but definitely a lot of center pressure relying on that, the 2 feet. with the heel being mostly involved on the right side, and then the forefoot being, what's maintaining that balance on the left side. If we were to then compare this, we could look at the differences between the foam and the firm surfaces. So let's go ahead and do that comparison. And this would be the ability to create that full best test where we've got both options in one report, and then allow us to score that individual and keep that for our documentation purposes as they're going through that rehab process. And again, it's taken a long time to generate these past couple days, but that's okay. We'll keep it moving. Looks like there's already been a couple questions that have come in, so that's great. We'll definitely get to those here in just a moment. I've got one more application to discuss once this finally generates its report. I think in terms of this information, what's really interesting to then start to see and allow for is, of course, you've got access to the data in real time, so you can even utilize it as a biofeedback, allowing people to play around with not only biofeedback from an EMG standpoint, but then the biofeedback from the insole standpoint as well. So here's this comparison where we're looking at the firm versus the foam surface. So we've got firm on the right, and we've got foam on the left. Interesting to see on the firm surface a little bit more of a higher pressure on that left side. So you can see that deviation actually going towards the left. And then some indication, of course, of the EMG. For the firm surface on the pressure print, we can see a much tighter center of pressure circle here compared to the foam surface, where there's a lot more of that anterior-posterior movement. And then similarly with the tandem test, it's definitely much more reliant on that left foot, whereas there's a lot more variability occurring on the foam surface just from all of the moving around there with the eyes closed. If I take a step back here, and I actually recorded this with so this was with the dominant leg. If we look at it compared to the non-dominant leg, this is where you can start to see some interesting things as well. So let's take a look at that real quick. So with that non-dominant leg, and in particular, let's actually look at them side by side. So I think what's interesting here is to then start to look at, okay, how are these pressures, oops, this is left first, right, yep. How is this individual handling balance on this single leg? You can see on the left side, the dominant side, that there's much more quad activation that's occurring. This person is utilizing that quad to help stabilize and keep that balance in check. We can even see how that relates then to the center of pressure once it enables here. And we can look at the control of this individual to be able to maintain that balance on the left side. And let's just zoom in on these signals. But if we look and we play these back, and let's look at it in slow motion here. So with that quad involved, you can see that they're able to control and keep that center of pressure kind of in that midfoot range, a little bit of pressure up at the toes, but in general, a nice tight circle. Whereas with the other side, we're seeing a heavy deviation basically going all the way up and down the foot, and a lot more significant ankle activity as well. So trying to maintain that stability just with the soleus, and very much less with the quad, being involved here. You can even see some of those time points where even the trunk starts to get involved as well, a little bit in both, but in particular on the non-dominant side, you can see some of these spikes here where some of that movement is having to be corrected by the trunk. This would just be an example of understanding, okay, what's going on from a pressure standpoint, and how does that then relate to something else that's going up the chain from the from the muscle activation, for instance. So finally, if we take a look at one more example of a recording, We can look at something a little bit more dynamic, such as cutting. Of course, you know, the nice thing about having it be part of this portable lab setup is that we're able to take it into different environments. So we can utilize it outdoors, we can utilize it in a gym, in the lab space. But you've got the ability to capture these different movements and really have that freedom to utilize them in different environments if you need to. So in this particular example, we're looking at some cutting activities. We can see I've got called out the knee flexion angles, but then we're also looking at the pressure information here. And then this gives us the ability to then create some reports where we can look at some certain kinematic aspects as it relates to the contact points as well. So in this case, what I'm going to use is our point of interest report. And you can see that I've highlighted these particular points in time based off of the knee flexion angle. So I'm looking at that peak knee flexion as we're going out of the cut, so exiting the cutting movement. One thing that you'll notice in particular with this individual is that we have a very much a push off on the right side with that toe in that first metatarsal. Whereas the left side, it's a bit more of a flat foot approach. I think what's interesting to see then is how the kinematics relate to that as well. So in this case, you can see the peak knee flexion exiting that cut with that flat-footed approach is only about 49 degrees, whereas, you know, when we have the you know, the push off coming from the forefoot, mostly, we get a bit more of a knee flexion, which might allow us to create more of that momentum going into the cut and really sell or change that performance of the cut to help that individual who might be utilizing this in sport. Of course, we can then look at the discrepancies between the two sides and start to make some inferences or judgments so that we can train them appropriately or intervene appropriately, and then help them change that pattern so that they can have equal movement strategies or equal movement performance on both sides. As far as creating a report from this, then we could utilize something like the point of interest report. And we can step through here and we can pull, you know, disregard these images here. We'll focus on just the kinematics and the pressure from these images here, as well as the data from the kinematics. But again, we can see, okay, on that left side, a bit more of a flat foot approach. We've got contact at the heel and at the big toe, limited in our knee flexion, which we already identified. But then we can start to look at some of the other kinematics and how those are relating. These are all going to be the left-sided cuts, so you can see again that same style where we got more of that flat foot approach. Hitting about that 50 degree mark for the knee flexion. And some other aspects that we can look at might be, you know, looking at hip abduction, for instance, or even hip rotation. If we go down to the right side where there's a bit more of a powerful strategy coming off of that big toe, we can see, okay, we've got higher knee flexion, and we've got some movement occurring where we've got some internal hip rotation, allowing that center of mass to really follow where the cut is going. Whereas here, we've got some external hip rotation on that side. And so there's a little bit of a lag occurring when that individual is pushing off of that left side. They're not able to really sell that cut and you know, change direction as suddenly going from left to right as they are from right to left. So this again would just be an example of utilizing the insoles to understand that strategy of the loading, how they're accepting load, how they're transferring load in the dynamic movement, and then relating it to some of the other aspects of biomechanics, whether that be the kinematics or it's the neuromuscular strategy, for instance, like we were reviewing during that balance test. Of course, you know, the other applications that we can get into would certainly be running. We can look at the loading rates. We can look at the kinematics, the EMG as it relates to the plantar pressure distribution. And then, you know, we can look at load transfers in an ergonomic standpoint, and still be able to encapsulate and utilize this data to really give us a full biomechanics picture within the multi-device concept that we offer at Naraxon. So I'm going to go ahead and take some questions now and start to review those. We'll take a look at what we've got here first. Let's see here. So let's see, first question. So looking at temperature effects and compensation, the drift while remaining static, and durability. So as far as the temperature effects and the compensation, I don't have that technical data. I'll have to look that up, but I will send that over to you, Alan, and actually we'll be able to put that up on the website so that you'll have that. That would be coming from the manufacturer, which unfortunately I forgot to put onto my spec sheet. As far as the drift during static capture, you can see there that I mentioned during the technical specs that we're seeing less than 3% drift in full scale, less than 3% error in full scale, and then less than 5% between the variation between the different sensors. And then as far as durability is concerned, of course, we've got the life cycles, or the expected life for these insoles at the 500,000 load and unload cycles for light impacts, and about 50,000 load and unload cycles for the heavy impacts. So it really depends on what you're doing. If there's something that there's heavy shear forces involved in an application like cutting, that can obviously have an effect on those resistive sensors. So it'd just be something to pay attention to as you're utilizing the system and seeing if that data starts to deviate or becomes errant in any way. Of course, with the load time curves, we are normalizing them to body weight, so it should help alleviate some of the effects due to the drift and the durability. But you'd be able to see some issues, in the pressure print animation if there was anything going on with one of the sensors. Let's see here. We've got a question for, is it actually 8 sensors, or do we do some data mapping? It is physically 8 sensors, 8 resistive sensors that are positioned on the insole. So if you saw the presentation there, I'll take a step back and we'll look at that setup. So these are the 8 zones. There are individual pressure sensors that are set up in this configuration here. Compared to something like F-scan or other systems, really the biggest difference between those systems might be the spatial resolution of the pressure sensors. So, I'm not sure what F-scan has involved in their insoles, but compared to, one of our other products in our offering, Metalogic, there's roughly 240 sensors inside of that insole. So we have, a much higher spatial resolution there to be able to capture, a bit more accurate center of pressure, as well as, individual calibration of the sensors to actually provide a absolute measurement of force. Our Ultium insoles are really meant to provide that qualitative information for loading, as well as the timing characteristics related to when the foot is on and off the ground. And then, one major advantage for certain compared to other systems is, the ability to utilize this with the multi-device setup. So that is what it's meant for. It's meant to be an accessory to the Ultium system, to utilize with EMG, to utilize with the MyoMotion IMU motion capture system, video, and be able to utilize the MR software to not only process the data, but then analyze and generate reports as we walked through a couple of the different options there. Let's see here. Can you discuss the effects of the wearer picking up various loads during manual material handling after system calibration? Will each external load be reflected in the max curve as a percentage above body weight? That would be expected, yes. So after the calibration of body weight, again, it's a quick calibration. You're standing on one foot and then standing on the other foot. That would be normalized to the body weight. So you would see when they're standing on both feet, roughly a 50% weight distribution to each side. If they were to pick up something heavy, you would see that reflected in those curves. And of course, how is that person accepting that load? Do they lean back onto their heels to hold onto that, or are they, balancing a little bit more with that full foot? Let's see here. Does the type of shoes interfere with the readings, like Hoka shoes? So of course, within any in-shoe measurement, you're going to have some effects of the shoe, and mostly that comes from potentially the shoes being too tight. So pulling the insole onto the foot such that you get these phantom pressures that might occur when the individual is actually not in contact with the ground. As far as types of shoes like the Hokas, for instance, which have a bit more of a soft cushiony effect to it. The idea of having the in-shoe option is to really understand how is the foot interacting with the shoe, not necessarily how is the shoe interacting with the ground. So you would be able to potentially see some dampening. You might see that the impacts from while you're walking or running might be reduced with a shoe like the Hoka. And I would say that's a great example of how to use these insoles, is to be able to differentiate between, somebody's strategy when they're wearing one type of shoe versus another. Let's see here. Does it need to be calibrated regularly? So again, the calibration takes place before each recording. You do have the option to do multiple measurements in a row, in which case you wouldn't have to do a recalibration. But if you exit that measurement, then you would have to do another calibration. It really only takes about a couple seconds. Let's see here. Question about durability. It's more interested in the SmartLeads coming out of the shoe and where they are sensitive to bending and kinking. So the SmartLeads themselves, they don't have to be, you don't have to worry about bending them. So let's take a look at the presentation here. So we've got our insole here, and then this leash would be coming out of the shoe, and potentially you would just add a little kink right here to allow for some ankle movement so that the insole doesn't pull if there's any inversion or eversion of the ankle. And then you can position these two. This would be the transmitting sensor. This is the SmartLead itself, so that can be bent. And then the insole is certainly something that you would want to pay attention to in terms of bending. I believe the bend radius is, I want to say it's like less than 20 millimeters. I'll have to double check on that, but certainly something that you wouldn't want to fold in half, or even potentially wrap around something to look at pressure. In an ideal state, they should remain as flat as possible, and then of course the slight bends that occur during walking and running. With any insole system, especially those that are reliant on those resistive pressure sensors, anytime that they get kinked or bent, you'll start to see some errant measurements, and that's certainly something that will be picked up not only in that pressure animation, but then you'll also see some values that'll show up in those load time curves as well. Let's see here. Besides needing to purchase the insoles, what else is needed to implement in the system? Does it work with existing receivers? Is software included? Does it require the purchase of an updated software package? Great question. So these insoles are a SmartLead, which is an accessory to the Ultium EMG system. So it is required to have an Ultium receiver as well as Ultium sensors to be able to utilize this. As far as software is concerned, the support for the insoles is only available in the software versions of 3.16 or higher. So as we move forward, so that it would, if you are not using the 3.16 version, then an upgrade would be necessary to utilize this system. But more importantly, It is, it can certainly be used as a standalone system of just the insoles, but you would need the Ultium system to be able to capture that data. So it is not compatible with our former systems like the DTS system, for instance. Let's see here. So regarding the lifetime of the insole, so once the insoles start to degrade, which again you would notice within the data itself, at that point they are disposable. So you can throw them in the trash bin, and they're set up as far as cost-wise to be able to be an affordable system that you can continue to purchase with different funds. If you do have questions on specific pricing, please reach out to us after this, and we can help you figure out what configuration you might need and what it would cost. Let's see here. The maximum distance and the range between the sensor and the receiver, so that's going to be 30 meters for live transmission. However, the Ultium system is, each of the sensors is actually equipped with a memory chip. And so you're able to, if you do go outside of that transmission range or there's some sort of interruption in the wireless communication, it's going to store that data on the sensor, and then you can actually upload it to the recording to fill in the gaps at a later date, or directly after the recording if you want as well. So live transmission is 30 meters, but we do have the lossless technology built in there, so you don't have to worry about actually losing any data points. See, I think there was a couple other in the chat, so let me go ahead and pull that up. Let's see here. Is life expectancy tested with a machine or based on real walking with a live person? So the testing is done with a machine at the manufacturer level, and then we've done additional testing in-house with walking and running. And then extrapolated that data and utilized both of them to determine the general life expectancy for the light and the heavy impacts. Let's see here. A lot of concern with durability, and I think this was actually the previous question to the one that I answered earlier. So I apologize for not getting those in order. Let's see. The lead insoles are getting kinked. Okay, inserting or removing footwear. So the insoles themselves, again, putting them inside of the shoes, maybe they're boots, maybe they're running shoes, maybe they're working shoes. We've even had some requests with regards to like snowboard boots and skis. You definitely will have to be careful when you're putting them in there just to make sure that you don't bend the physical insole. But the actual leash here is not really a worry to be able to bend those around and fit them into the shoe as necessary. Certainly, you would just not want to actually physically bend it so that, this portion of the insole is folded over. You would want to try to avoid that as best as possible. But this portion of the insole, the leash and the actual lead, do have a lot of play and aren't going to be affected by that movement. It's really the sensors that you see here, and in particular, the portions of the insole where those 8 sensors are. So if we go back to this slide, so these portions here, that's where you would really want to avoid any sort of kinking or serious bending past that bend radius that we had discussed previously. Of course, avoiding that is not always possible. There's certain times where you're trying to get it inside of the shoe, and it's it's a little bit difficult. But I would say just being as careful as possible. You shouldn't have too much trouble there. All right, let's see here. Could this be used to see impact of surface friction on the ability to generate force? Looking at how changing a surface will improve stability to allow for upper body force generation. Very interesting. I'm not sure if you are meaning regarding to actually having that be on like the feet or where you would want to position those. But these are just measuring that vertical force component. So as far as looking at friction, in the plane of the surface, it may not really give you that much information. Of course, you can certainly use the pressure animation to see how that friction is being handled in the shear directions. But as far as the information that it's providing you, it's just going to be that vertical component. So I would say, like, from a stability standpoint, you know, very similar to that, the best test example that we were looking at, where we had a firm surface and then a foam surface, you certainly are able to see the change in how the pressures are interacting with the two surfaces. So, you know, in that firm surface, we were able to see significant stability, even during some of the single leg or the tandem stance tests. And then when we added in the foam surface, it got a little bit more shaky, and you could see how that individual was shifting into the medial, lateral, and anterior, posterior directions to really compensate for the movement of the surface underneath the foot. So if that's what you're looking for, then I would say it definitely is a great solution for that, to understand, you know, how the different surfaces change stability. But I'm not sure what looking at like friction or impact friction might be, how you would use these insoles for that application. Okay. Oh, one more. Yes. So with regards to the disposability of these, sorry, the insole is the only portion of the system that would be disposable. The SmartLead itself is not disposable. So this portion right here, so the connection to the insole as well as the connection to the sensor, that's a one-time purchase that you're able to continually use time and time again. So the only thing that would need to be repurchased, or, you know, have purchased in bulk, or, you know, whatever is necessary for your project, would be the physical insole. And of course, you could have multiple sizes as well as multiple pairs to be able to accommodate the use of those sensors over the course of an entire project. So this portion, the actual physical insole, would be the only thing that would be the disposable aspect of this system here. Okay. We'll give a couple seconds to see if any further questions come through. Looks like one more. So let's see here. I appreciate everybody for joining us today. I know we went a little bit further over our time. And yes, we will, for distributors that are online, we will definitely send some pricing. Otherwise, please contact us at info@naraxon.com, or if you are in contact with your local representative or your regional representative, you can always reach out to them for pricing as well. I appreciate everybody for joining us today. I hope you guys are excited about this new product, and, you know, you'll start to see some more stuff, more information come out about it with some posts online. We'll also be putting this up on YouTube and our website as well, so you can always watch this video at a later date if you want to have some more information, or revisit any of the information presented. I hope everybody has a wonderful rest of the week, and we will see you next time.